All right. Good evening, everybody, and welcome back to DC iOS for our first 2026 meetup. We're actually starting to get some speakers already lined up this year. I think we're going to have some exciting talks over the next few months, and I'm excited to kick us off. Hope everyone enjoyed their January off. It's nice to have a month off, especially because, as I said, I usually go to a convention that early time of January, so I was able to just rest and recover. And of course, most of us in the DC area were promptly snowed in for like the past week or so, and we still have piles of snow everywhere. So we all can wait for it to warm up. But let us, get right to it. I know our talk today is actually going to be very detailed and in depth, so I want to make sure we have a lot of time to be able to enjoy it and ask questions. So without that, without ado, I am going to hand it over to Will to take us through SwiftUI's internals and performance.
Hey everyone, I'm Will Downey. I'm a software engineer here at Capital One, and my presentation today is titled A Climb Up the View Tree. Like Scott said, we're going to be talking about SwiftUI internals and some performance at the end. So as a brief overview of what I'll be covering today, first we're going to be talking about state and binding, then we're going to move to view trees, we'll move to layout, and then finally a brief section on performance at the end. Okay, so let's start out with state. According to Apple, state is a property wrapper type that can read and write a value managed by SwiftUI. The state property wrapper allows us to modify values inside a struct, and this is important because structs use structs are value objects, so they adhere to value semantics. But it allows us to modify these properties like they were in an object that is a reference semantic object. So this is a little abnormal, and we'll cover this later in the presentation. If you need a little primer on value objects versus reference objects, value objects in Swift are immutable. So structs are value objects, classes are reference objects. Copying a value object gives you a new object. Copying a reference object will give you the same object. Moving back to state. State allows SwiftUI to create and destroy our view struct without losing the view state. So as state is changing and we need to create new instances of views, we're able to persist our state across those different instances of views. State is also used to track local changes. So state will generally always be private and initialized on declaration. That's a good rule of thumb to follow. State will not track changes to reference type. So we can think of variables storing instances of reference objects as pointers to an address in memory. And so SwiftUI won't be able to track changes because that pointer is not changing. So we can get around this by using observable and observable object. And again, we'll cover this a little later in the presentation. Then finally, SwiftUI tracks where a view is affected by state change and makes relevant updates. SwiftUI is pretty efficient at finding where it needs to redraw views based on state changes. Okay, so let's look at an example. Typically, we would use state like this. Here we have a struct that conforms to the view protocol. So this is our view. We've called it number generator. We have one state property on this view called number. Number is an integer. And like I said before, number is private to the view. So it's local to the view. And we've initialized it on declaration. So we've given it a value of 0. Our view has a body here. It has a button. And so the button is going to execute a closure when clicked. Then it has text below that button that's going to display our state. So when we click this button, we're going to update our state with a random integer between 0 and 100. And the idea is that SwiftUI is going to be able to track that change and know that it's going to redraw the text object at the bottom. And so we're going to have an updated text object with our number. Okay. So as an overview, without this property wrapper, we wouldn't be able to modify this value since it's initialized to 0. Like I said before, value objects are immutable in Swift. And so if we wanted to modify the number property and it wasn't using the state property wrapper, we would have to create a new instance of number generator with the updated number property. Whenever this button is tapped, state is going to be updating SwiftUI, or state is going to be updated, and SwiftUI will know to rebuild the view. And so it's going to redraw the text view we have at the bottom here. So clearly from this example, we can see that SwiftUI is using the state property wrapper to perform some kind of magic under the hood. But we might be wondering about what state is doing and how we can use state in SwiftUI. So looking at the second example here, this is the exact same as the first example, but this time we're not using the state property wrapper. We're manually creating our state. And so this time we have an underscored variable called number, and we're initializing it to state with an initial value of 0. So this is analogous to what we're doing beforehand. And we've also provided a property wrapper integer just called number. And so this is purely for convenience. This allows us to access our state by just typing number instead of typing _number.wrapped value. We can see the getters and setters for this computed property are just accessing the number's wrapped value. So we can see here, you might be noticing there's a little bit of weird syntax here with this non-mutating set. And so what the non-mutating set does is it tells us that when we're assigning to this computed property here, it's going to create a new instance of the number generator struct, and it's going to be updating the _number.wrapped value. So every time we're assigning to this computed property here, it's going to use non-mutating set, and it's going to be carrying a new instance of number generator with the updated property. And so that way we're not breaking our value semantics. Okay, so now we're creating the state object manually. We're using _number. We're providing a computed property as a convenience. That's not necessary. And this allows us to type number instead of _number.wrapped value. We can see here that this view is the exact same as before. So the view body is the exact same as the previous example, but we're just creating our state in a different way. So the state property wrapper allows us to achieve all the same functionality we have here, just in a more concise and easier to reason about way. So if we go back to the previous slide, these two perform the exact same, but we can see there's much less code on this slide compared to the slide that we're currently on. Okay, so now we have a general understanding of state and how we might use it in SwiftUI. But what happens if we want to share state of one view with another? You might imagine a scenario where we have a parent view and a child view, and the parent view is holding on to some state. And so the parent view wants to pass that state to the child view, and the child view wants to update the state, and we can track those changes in the parent view. And so, like I said, state is normally going to be local to your view and private. So we need something else to track changes between different views, and that's where binding comes in. So, like I said, state is used for the view to react to local changes within the view, so it's typically private. But if we want our view to react to changes to other view states, we can use a binding. So we can create our state in one view, and we can use a projected value from that state to get a binding, and we can pass that binding to another view. So binding allows multiple views to share a single source of truth, so this is extremely powerful for us. Okay, so now let's take a look back at our first example. This time I've modified a few things. I've changed the state property wrapper to use binding. And this time you can see that I've removed the two requirements for the rule of thumb I mentioned using state. So binding is no longer private, it's internal here. And we haven't initialized number on declaration. So we don't have a value for number yet. So what that means is that Swift is going to automatically synthesize an init for us. And so when we're creating number generator, when we create an instance of number generator, we're going to need to be passing in a binding to an integer in order to create this number generator. Okay, we can see here our view body is the exact same as before. We're accessing number. We're updating number with a random integer between 0 and 100 when this button is clicked. Okay, so this is an example of how we might use our number generator 3 from the parent view. What we've done here is we've created the state on the parent view. And like I said before, it's private and it's initialized on declaration. We have our body here, and we're just creating a number generator 3 struct inside our body. And you can see here we're using this $ syntax. So the $ syntax allows us to access the projected value of state. And so this projected value is going to be a binding. So we're passing in a binding to our child view, which is this number generator 3 struct right here. Yeah, bindings are really simple. Bindings just wrap the getter and the setter to a wrapped value. So typically it's our state. So it's going to be our state's wrapped value. And like I said before, we can use the $ syntax. You don't have to worry about that too much right now, but essentially it allows us to easily access the projected value of our state property wrapper. Okay, so now we have a decent understanding of how state and binding might work, but we might want to learn a little bit more about how these work in practice. And to do that, I'm going to have a live demo where I'm going to be re-implementing state and binding from scratch. So this is mostly conjecture, and it's mostly a best guess or best effort guess at how Apple might have implemented binding and state. But these are going to be pretty simple. It's not going to have the full implementation, but at the end of this demo, we will have a working state that will be tracking changes to our view. Okay, so before we get started in this demo, I want to do a little bit more of a detailed example on reference versus value objects. And to do that, we're going to use this view here. So this is a struct here. It's test, so struct test, and we've conformed it to view. So this is our view, this is our test view right here. And we have a property on our test view called text. And so you can see here, we're not using the state property wrapper. We're just assigning this. We just have this property as private, and we're just assigning it to an empty string here. And then we have a very simple body. But inside the body, inside this button, what we're trying to do is mutate a property of our struct. And so since structs are value objects and value objects are immutable, we're getting this error from the compiler saying cannot assign a property, self is immutable. So this is why we need state. And this is why I said in the first slide that state allows us to use properties of value objects as if they were properties of reference objects. And if we jump down to the second example here, we can see that we've replaced our struct with a final class. But other than that, it's the exact same. So we still have that same property. And this time we have no compiler error. We're actually able to modify the properties because we're using a reference object here. Okay, awesome. So now that we have that out of the way, let's move into our implementation of binding first. Okay. So like I said, binding is really simple. It just wraps the getter and setter to a property. So we can see in our property wrapper struct here, we have a simple computed property. It has a generic type value, and it has a getter and setter right here. And so again, we're using this non-mutating set. So when we assign things to our wrapped value, we're going to be creating a new instance of my binding. The getter and setter are relatively simple. They're just accessing closures that we have stored on our struct here. So the get value is just calling the get value closure we have stored, and set value is just calling the set value closure we have stored. And so we can see those stored right here with our private let get value and private let set value. And then our init is also quite simple as well. We're just setting the get value and set value for this struct. And we can see finally at the bottom here, we have a projected value. So if we were to use the $ syntax, this is what we would be getting. You can see it's type self, so we're returning a binding. So the projected value for bindings is just a binding. Okay, so you might be wondering why we even need to use state if we can just use binding for everything, right? It seems like binding wraps the getter and setter to our property, and so that's all we need. But we can illustrate why we need state with this simple example right here. So you can see if we're trying to create a view using the binding we've just created, we were passing in closures to get value and set value. So get value is just returning my storage, and set value is just assigning to my storage. But we'll notice that we have this my storage global variable here. And so the reason why state is useful is because it wraps both the storage for a value and the binding, which remember the binding is the getter and the setter for a value. So we have all three things. We have the storage, we have the getter, and we have the setter for value. And so that's why state is really useful for us. Okay, so yeah, like I said, state solves our problem, and let's take a first crack at implementing state here. So this time, for ease of use, I've just decided to use a class for our first implementation of state. And we have a wrapped value here. So this wrapped value has a generic type v. We have a binding on our state. So this binding is using the my binding we've just created. And it has get value and set value. You can notice in the get value, we're just returning our wrapped value. And in the set value, we're just assigning to our wrapped value. The init is even simpler. We're just assigning value to our wrapped value. And then our projected value, which we can access again by the $ syntax, is just returning a binding. Okay, so now let's try to use our state like we would the state property wrapper from SwiftUI. Cool. So in this small example I have here, we have two different states. We have one which is a Boolean and one which is a text. And then we have a button inside our view body here. And so ideally what happens here is that we're going to be clicking a button. It's going to be switching our Boolean state. So it's going to be toggling our Boolean state. So if it's true, it's going to switch to false. If it's false, it's going to switch to true. And then based on the value of is on, we're going to set text to two different strings. So if text is true, we'll set it to hello world. If it's false, we'll set it to goodbye world. And then inside here, we're also printing text just so we can see updates to our state. Okay, and then below this button, we're just outputting what the text is. So ideally, on this preview here, when I click this button, the text is going to alternate between hello and goodbye world when we're clicking it. And we can click here, and I'll clear out my console just so we can see even clearer. So when we click between these, we can notice that while our prints are reflecting that the state is being updated, it's not actually reflected in our view. So there's a couple more things we're going to have to do to get SwiftUI able to track updates from our property wrapper. Before we do that, though, we probably want to solve the problem of using a struct instead of a class. So if we go Sorry, trying to type with one hand. So if we go to Apple's signature for state, we can notice that Apple uses a struct and they don't use a class for the property wrapper here. But you might be wondering how they can get around using a value object when we're mutating a property of that object. And so the way Apple does this is through having a class that belongs to our structs here. So we have this storage class here. And inside of storage, we're just storing a value. And then in the init, we're just setting a value, or we're just setting the value. And so then we hold a reference to this object on our struct here. And you can see in the wrapped value, we've changed a few things. We've updated our wrapped value, the getter and the setter of our wrapped value, to access the storage's value, not the wrapped value that we're storing on the struct itself here. So this time, we're accessing the value on a reference object that we've stored on our value object here. And so the rest of this view is pretty much the same here, or the rest of this property wrapper is pretty much the same here. We have binding, and so it's just getting and setting the wrapped value. And so again, when we're calling the get value and set value of wrapped value, this will actually be calling the getter and setter of wrapped value. So our binding is just calling the getter and the setter of wrapped value, which in turn are accessing self.storage and assigning self.storage. And then again, we have our projected value, same as before. So now let's look at our second preview. This is the exact same as before, but this time we're using myState2. So our second implementation of state. The main difference this time is that, again, we've switched from a reference object as a class, and this time we're using a value object, which is a struct. And so we can see here that there's no changes to our view. We're just changing the property wrapper here. And if I go ahead and clear out my console, so if I go ahead and clear out my console here, we can see that as we're hitting the button, same behavior, right? We're still not getting any changes to our view, but we're seeing changes in the view state. So now we're a little bit closer to what SwiftUI's implementation might look like, and we just need to put the final touches on. Okay. So we need to make two changes to get SwiftUI to be able to track our view. The first one is adding dynamic property here, adding a conformance to dynamic property. And the second one is making our class observable. So like I said before, SwiftUI isn't able to track changes to reference objects. And since we have a reference object stored on our view here, we need to make this class observable so that changes to the properties of our storage class are published. And so we're going to have an observer on the properties of our storage class, and these changes are going to be published, and that allows SwiftUI to pick up these changes and reflect them in our view. So if we move on to our third preview here, again, everything's the exact same as before, and the rest of this body is the exact same. We've just added observable, and we've added the conformance to dynamic property here. So we'll look at our third preview here. Same as before, using the myState3 property wrapper this time instead of myState2. And we can see as we're clicking on this button, the view is working correctly. So now we're switching between hello and goodbye world, and we have a working implementation of state. Okay, so this is a fairly trivial example, and things are pretty simple here. I wouldn't recommend that you use this implementation in your applications, but hopefully it gives us a good sense of how Apple might have implemented state and binding, and a good reference to how we might use them in our app. Okay, so let's jump back over to our slides here. And that's going to conclude our section on state and binding. Next up, we're going to be talking about view trees a little bit. So view trees are a way about thinking of SwiftUI views. Understanding view trees is crucial for us to write efficient SwiftUI code where we're minimizing our number of redraws and our number of state changes. It's important to note that view trees are different than attribute graphs. So if you're familiar with attribute graphs, that's great. View trees are a separate concept, and we'll be covering what attribute graphs are later in this talk. Okay, so let's consider the following very simple view. We have a text view here, and we're just calling a single view modifier on it, padding. So what's important to know about view modifiers is that every single time you're calling a view modifier, you're actually returning a different view. So in this example right here, we're actually creating two views. We create the text view first, and then we call padding on it, and then that returns a separate view. And so we can think of each view modifier in our view as a different station in an assembly line. So we start off with our product, which is just the text. We go to our next station, which is the padding. And then you can imagine if we're calling modifiers after that, those are our next stations. And so as you might infer, the order that we're going to these stations in our assembly line really matters. And so if you're more of a math person, you can think about this as like order of operations. So we're evaluating the views top to bottom. And so each modifier, we're evaluating the products before and passing in a single product to the modifier, and it's outputting a single product. So for example, we're evaluating text first, we're passing that to our padding view modifier, and then our padding view modifier is outputting the text with the padding. Okay. If we take a look in the bottom right corner here, we can see our view on the left side and our view tree on the right side. So for this view, it's an extremely simple view. We just have two nodes in our view tree. First is the padding view, which is the parent, and the text view, which is the child. And so one thing you're going to want to know about view trees is that the last modifier you call is always going to be the root of your view tree here. Okay. Let's move on to a slightly more complicated example. So this time we have the same view, but we've called the background modifier after that. So we can imagine in our assembly line mental model, we have our text first, and then we have our padding as our next station, and then our green background as our final station here. And so if we were to change the order of these stations, we would actually get a different view because we're applying the background before the padding. A common beginner's mistake with SwiftUI is thinking that all the modifiers are applied at the same time. But really, it's helpful to think of them as an assembly line, like I mentioned, or as an equation with order of operations. So we're slowly building up the view. Each time we're applying a view modifier, like I said before, it's getting wrapped in another view. And we can read our chain of view modifiers from the bottom up to get our view tree. So like I said before, the background view is going to be the root of our view tree here because it's the last view modifier called. In the bottom right, we can see our view. And so we realize that this view has padding applied first and then the green background. So we have a pretty big green background because it includes our padding. And the view tree for this view kind of gives us a clue as to why that might be. So first, we have our background view as the parent view. We can think of the background view as wrapping the view with the background we're provided in a Z stack. It doesn't exactly work that way, but that's helpful for our mental model. So we can see the background view as a parent, and then we can imagine that it's wrapped its two children, the padding view and the color view in a Z stack here. And so again, our padding view has one child, text view, like it did in the previous slide. Okay. And so now we can see that if we flip the order of these view modifiers, we actually get a different view. And the reason why is because the view trees change. So going back to our assembly line mental model, if we change the order of our stations, we're going to get a different output because we're applying the green background before the padding. This view trees, as you might expect, we have padding as our root, and then we have background. And again, we can imagine background as wrapping in a Z stack, the text and the color children views. Okay, so some learnings about view trees. Modifier order matters. Like I said, we're changing the order of our stations in our assembly line. So that's going to change the outputted view tree, which in turn is going to change our SwiftUI view. Like I said, we can use the mental model of an assembly line where each modifier is a different station in our assembly line, and we're slowly building up our view for the final product. If you put one station before the other, you can imagine on a car's assembly line, if you put on the axle and then the wheels and then you put on the frame, it would be a different output than putting on the wheels and then the frame and then the axle. That might not even work. And the assembly line at each station, we're wrapping a different layer. So at each modifier, we're outputting a separate view, and the last view modifier is going to be the root of our tree. Okay, so we'll come back to view trees in a second, but for now, let's introduce view builders. View builders are built on top of Swift's result builders feature. View builders are a special syntax for a closure that creates a list of views. And we can get a little hint into how view builders are able to do this by looking at the view builder signature. So here at the bottom of the screen, I have the view builder signature. We have two different function signatures I've decided to include here. The first one is the build block, which is going to be when we're building a list of one view. And the second is the build block when we're building a list of an arbitrary number of views. So we can notice there's a few differences between these two function signatures. The first one, we're taking a generic parameter content, and we're enforcing that content has to be a view. And we're just outputting that type content. So you can imagine if we're creating a list with a single button, the output type is just going to be button, right? But in our second function signature here, we're using a new feature of Swift as of Swift 5.9 called parameter pack iteration. And so if you're not familiar with parameter pack iteration, it's these repeat eaches that we have in our function signature. This allows us to iterate over an arbitrary number of generic arguments. So this function signature is valid for an arbitrary number of generic types. So if we can think of an example where we have a list of a button and a text view, our generic types here in our angular brackets are going to be button and text. And then in our content, the arguments we're taking are going to be of type button and text. And here, we're not just returning a single type, but we're actually returning a tuple view. And so this is how SwiftUI creates list with multiple views. And so the tuple view is going to have a type of a tuple of the button and text types from our example. And so for our mental model, we can think of these two different function signatures as creating the same thing. So we can think of the first function signature as creating a list of just one view, even though it's just outputting that view itself. It's not really returning the list, which would be our tuple view. Okay. View builders are used everywhere in SwiftUI. If you're not familiar with them on the surface, one thing to notice is that the body of every single SwiftUI view is implicitly a view builder. So they're really used everywhere. And one thing we want to consider with view builders is how using view builders can affect our view trees. View builders can actually apply modifiers differently to their children. And so that can affect and cause some unintended consequences of using view builders that we'll cover in the next few slides. Okay, so before we get to our examples, we're going to introduce group real quick. So group is in a nice abstraction around view builders. For our purposes and for our examples, we can think of groups as just view builders. And like I said, group provides a really nice API around view builders. So group is a view, but it takes one argument on its init. And so that's just a view builder. So we can think of that as a list of views. Okay, now that we understand group, let's move to our example. So this is a very, very simple example right here. We just have a single group and one text object inside our group. So we have a list of one view. It's just text. And we can see our view tree is correspondingly very simple. It's just group as the parent and text as the child view. And so if we go back to our function signatures, we can infer that we're using the first function signature here because we're only passing in one view to our view builder. But if we jump to a more complicated example where we have two views, so this time we have two different text objects in our group. And if we jump back to our function signatures here, we're using tuple view this time. And so we're going to have a different output in a different view tree. So this time we have a different view tree than before. And so this time we have group as our parent, we have two child tuple views, and then as the children or the leaf nodes of those tuple views are going to be two text objects. And so these view trees seem very similar and they kind of behave the exact same, but it's important to know that SwiftUI is doing something under the hood to build lists with multiple different types. Okay, so notice how when we use a single view, it's just treated as if it was a standalone view and we're passing it into a view builder. But multiple views are wrapped inside the tuple view. So doesn't seem like it has big impacts yet, but let's take a look at how our modifiers are impacted when we are applying them to our views. Okay, this is our more advanced example from before. Here we have the group with the two text objects, but this time I'm calling background green on the whole group. And so you might notice from our view on the left side here that our background isn't applied to the entire group as a whole. It's actually almost as if it was applied individually to each of the text elements. And so this is because container views like group or even HStack, you might have noticed displaying this behavior, they unfold lists. You can think of like a compact map from functional programming. It unfolds lists into a flat list of direct child views. So even though we have our tuple view and our view tree here on the left side, we can kind of think of it as background view having three direct children, the two text views and the color view. And so these background modifiers or any other modifier we call in this group are going to be applied like they were applied individually to the text views, which is kind of an interesting functionality and something you might not notice. And this actually works the same if we put an HStack here instead of a group. So it's not just unique to the group API. Okay. So now we have a decent understanding of view trees and a decent understanding of view builders. And so let's talk a little bit about attribute graphs. In the beginning, when I introduced view trees, I said that view trees are different than attribute graphs. And so you might be wondering, what even is an attribute graph? And so attribute graphs can get pretty complicated. As we can see on the bottom left-hand corner here or the bottom right-hand corner here, this is an attribute graph for an extremely simple application. So attribute graphs are very hard to wrap our head around and can be very complicated. And so to avoid all that complication and to make things a lot simpler, I'm going to visualize attribute graphs in the next few slides as a tree. And I've removed state and dependencies from the attribute graphs. So in contrast to our view trees, attribute graphs include state and dependencies of all our views. And so I've just removed that all from the attribute graphs and I've visualized them as view trees or as trees. And so, but we can see in reality that an attribute graph is really a directed graph. and it is including the state and dependency. So it's important to know what I'm going to show in the next few slides is not actually what an attribute graph looks like. It's just really to help our mental model of how SwiftUI is building up these views and what the attribute graph might look like in a simplified version. Okay, so attribute graphs is Apple's internal framework for efficiently tracking view updates. We can think of the view trees that we talked about previously like blueprints. So blueprints are created every single time we're creating a view, and every single time we're updating a view, and they're just thrown out every single time. So every time we change a view tree's thrown out. We're going to draw a new view. So we're starting from scratch. We're creating a new blueprint. Attribute graphs, like I said, track view, state, and their dependencies. So now they're including state and the dependency. So, all right. Now they're including the state and the dependencies of the views. And like I said, for simplicity, we're going to visualize them as trees. Sometimes some people like to call these render trees. So you might have seen that in books or blog posts before. But really, when they're saying render tree, they're talking about SwiftUI's attribute graph. And like I mentioned before, view trees are constantly being reconstructed. Every single time we're rendering a view, a new view tree is going to be created, but the attribute graph persists across these re-renders. So the attribute graph is going to stay constant, and we're going to be adding and removing nodes as our views change. So let's consider the following view and its corresponding view tree, and we'll see how that differs to the render tree or the attribute graph for this view. So this is a very simple view here. We have a state property called Meetup, which is an optional string. If this string is nil, we're going to be showing a text in our view. So inside the body of our view, we're wrapped everything in something called mirrored view. And so mirrored view is a helper that I've created that uses the mirror API from Swift. So it uses reflection to allow us to check runtime or check objects at runtime. And so that's what is allowing us to construct these view trees that we've seen in the previous few slides and this slide. And so otherwise inside the view, we have a simple group and we have 3 text objects. So we have hello text, and then inside a if let, we have a text that's just outputting the state we have, and then we have an exclamation point after that. And so the idea with this view is that when our state is nil, we're not going to be showing the middle Meetup. And when our state is non-nil, we'll be showing that middle view. So it will say, hello, DC iOS with an exclamation point, right? But right now it's nil. And so we can see in our view tree here, we have a group as our parent, 2 tuple view children, and that last tuple view has 2 normal text objects as its child, but 1 optional text object. And so we can notice that even though this text object that's optional is not included in our actual view, like it's not actually shown in the view here, it's still included in our view tree. And this is important when we look at a render tree or a simplified attribute graph. So we can see now that the attribute graph does not have the optional view in its view tree or in its tree anymore. And this is because the attribute graph is it's a more realistic example of what's actually being shown in your view. So nodes can be removed and added to the view as we're removing views from our body here. And so right now, the state we have is nil. And so we're not showing this view. But if we were to change our state and give our state a value of DC iOS, we can see that we've updated the view. So it says, hello, DC iOS now. And we have our text that is now appearing in the view tree again. And this time, notice it's not optional because there's no concept of optionals in the render tree. Okay, so that kind of illustrates some of the basic differences between view trees, render trees, and again, render trees are really just the attribute graph. Okay, that wraps up our section on view trees, and I'll be moving to our 3rd section on SwiftUI layout. So layout is the algorithm for how SwiftUI decides to place views on the screen. And so a really basic version of this algorithm is that the parent is going to send a proposed size to a child view. If that child is itself a parent, it's going to recurse down the tree until we hit a leaf node proposing size to its children. So if we go back to our render trees, we can think of the parent view starting off, and it's going to propose a size to its child, and we're slowly going to recursively propose sizes down until we hit the leaf nodes of our children. And then once we hit the leaf node children, the children are going to be receiving that proposed size. It's going to calculate the size it needs, and then it's going to send that back to the parent. So the subview calculates its size and it sends it back to the parent. And what's important to know is that parents can never determine a subview's size. So a parent can only repropose a size. So if a parent proposes a size to a child, the child calculates the size it needs and sends that back to the parent, and the parent doesn't like that, all it can do is repropose a new size to the child. And so in SwiftUI, all of our built-in SwiftUI views behave differently, and they can actually change their behavior based on the modifiers applied to them. So that can affect our layout. And so different SwiftUI views are going to calculate their size differently, and they're going to return that calculated size differently to our parent. So it's important to play around with your views and to know that not all the built-in views in SwiftUI are going to be calculating their size in the same way, especially if you're calling some view modifiers on them. Some other things to note are that the root view always starts with the safe area screen as its proposed size. So we're always starting with the entire safe area screen. And parent views can propose a nil size to children. So SwiftUI views have something called intrinsic size. It's also a concept in UIKit. And so when a parent decides it doesn't need to propose a size to a child, it can just propose the nil size, and then the child can do whatever size it's happy with. So every view has a intrinsic size, which is kind of a size that it's happy with. So we can imagine for a text view, maybe it's like 300 by 200, right? And so my text view is very happy, it wants to be 300 by 200, right? And if we propose a nil size, if the parent proposes a nil size to that child view, it can basically say, okay, I've got the size I want. I've got my intrinsic size, 300 by 200, and it's just going to return that to the parent, and that will be our view. And then finally, as we made it all the way back up to the parent, so as all the children have calculated their size and returned that to their parent, and we keep recursing up our tree until we hit the root view. When that all is done, the parent's then going to start placing subviews. So then we'll get the actual layout on the screen, and we'll see how all our different views are laid out on the screen. And so a lot of that's pretty abstract, and we'll move into some examples. But before we do that, we need to understand alignment. So views in SwiftUI are aligned based on the views they share space with, and that determines how our views are laid out on the screen. Center is the default alignment for most SwiftUI views. To calculate center alignment, what we do is we calculate the center of the view, and then we calculate the center of the frame that view is in. And then we place the center of that view at the center of the frame. And so I've included a very simple equation to calculate the X and Y coordinates here. And so let's take a look at an example of doing this. So here we have two views. Again, we have our Hello DC iOS text, which keeps showing up throughout this, this presentation. And we have a 100 by 100 gray square here. And so I've made a view modifier that's custom that allows us to see the alignment guides for these different views. And in orange at the top here, we have our alignment guides finding the center for the Hello DC iOS text view. And then on the bottom for our gray square, we have blue alignment guides finding the center of that view. And so now when we want to have these two views share space in a Z-stack, what we can do is the Z-stack is going to by default have horizontal alignment of center and vertical alignment of center. So it's centering it in both the X and Y directions. And so since color is the biggest view in our Z-stack here, the Z-stack is going to be the size of color. So it expands to fit the size of the biggest view, which again is our gray square. So we have a 100 by 100 Z-stack, which is the same size as our gray square. We calculate the center of that gray square. So we find it here, it's probably 50-50, right? And then we calculate the size of our text view here, like we did before, and we're placing the center of the text view in the center of the gray square. And so that way our views are aligned both horizontally and vertically. And so there's a few different alignments that SwiftUI provides. There's vertical alignments and there's horizontal alignments, and we can combine the two to get alignments in two directions. So our vertical alignments are top, center, bottom, first text baseline, and last text baseline. And our horizontal alignments are leading, center, and trailing. And so we can combine those to get top leading, top trailing, bottom leading, and leading text last baseline, and trailing first text baseline. And so this covers most of our use cases that we would need alignments for. As you can see, I have a visual of like where all the alignments correspond on a view itself. But there might be certain scenarios where you want to get a little advanced and you want to have an advanced layout. And so to do that, you can use custom alignments. And so SwiftUI provides us a lot of flexibility here. To create a custom alignment, we just conform to the alignment ID protocol, and then we can extend horizontal or vertical alignment or both to add our alignment. Okay, so That covers most of our bases for alignment and shows the different alignments that are possible with SwiftUI views. You might have noticed that instead of using left and right, Apple uses leading and trailing. And so I have a question for the audience. Does anyone know why Apple uses leading and trailing instead of left and right?
Internationalization.
Yeah, exactly. So some different locales don't read left to right. And so leading and trailing can actually flip based on your locale. Cool. Okay, so now we understand our alignments and we have a general idea of the alignments possible for us, but how do we actually apply these alignments? So typically alignment is applied to all components inside a view builder or inside a grouping view. And so for VStack, we have alignment. We have an alignment parameter we can pass in. Same with HStack, same with ZStack. And so typically when you pass in the alignment parameter, it's going to apply to all the views inside that grouping view or inside that view builder. So in our case, we have an HStack with center alignment. HStacks align in the vertical direction. VStacks align in the horizontal direction. So it's important to know when I was talking about horizontal and vertical alignment, HStacks can only take the alignments in the horizontal direction. VStacks will only take alignments in the vertical direction. And so this center horizontal or the center vertical alignment is applied to both the text views by default. And so if we want to change that behavior for one of the views in our list, we can actually do that using the alignment guide. And so when we use alignment guide, we're going to have to use the alignment that we're using for our grouping view. So in this case, we're using vertical center vertical alignment here. And so we're going to need to override the center vertical alignment using our alignment guide. And in this case, we want to offset this second text by 20. And so we can see that reflected in our view here. We've overridden the vertical alignment or the center vertical alignment by 20. And so our hello world and then DC iOS is offset because we, again, have overridden the center vertical alignment and provided it an offset. Okay, that concludes my basic section on alignment and layout. And now I'll move into the final section, which is performance profiling. So for the purposes of this demo, I've actually created an application. And so I'll go through a brief screen recording here. So this application I've created is a simple Hacker News client on iOS. And so it fetches a bunch of different stories from Hacker News. And if you're not familiar with Hacker News is, it's a old school style forum where it has a bunch of different posts that people post. And typically when you click on a post, it links out to another website. So people will find interesting articles that they found online and they'll post them on Hacker News. And then on Hacker News, you can comment and upvote different articles. And so I've created an iOS client for our Hacker News website, and I have fetched these different stories on Hacker News from the Hacker News API that's provided publicly. And so as we're scrolling through our feed here, we can see that we'll notice a little bit of lag as we're scrolling through the feed. And so this is a fairly simple application, and obviously there really shouldn't be any lag scrolling through just a few articles. And I've actually limited to 200 articles. So clearly there's something wrong here because we really don't have a lot visually going on our view. Yet we're seeing a lot of lag as we scroll through our view. Also, I've added to the application, sorry if I jump back here, you can see at the end, I've added the like functionality as well. So we can like different stories and we can actually jump out here. So yeah, we can see you can like and dislike stories. You can also jump out to a web view and then jump back into the app. Okay, so again, still not a lot going on here. Really simple application, yet we're seeing lag as we scroll through our view. And so that's obviously not something we want. And so to fix that, we can use the powerful tools provided in Xcode for us via instruments. And so if you've never used instruments before, the easiest way is to build your application for instruments. So you can do that by hitting Command I, and it's going to go ahead and build my Hacker News application. And this will take a second, and then I'll be prompted with an instruments panel here. And I can choose what type of profiling I want to do. So for my case, I want to do SwiftUI profiling, right? Because I'm only using SwiftUI in my application. And clearly there's probably some view updates, unnecessary view updates, maybe heavy view updates in my application that are causing lag as I'm scrolling through the application. And so for my case, I'm going to click SwiftUI. I'm then going to hit choose. For now, I'll cancel out. But if you were to actually profile your app, you would hit choose. And for this demo, I've already recorded my traces. But if you were to record your own traces, after you hit choose that previous button on the screen we just saw, you'd be greeted with this screen and there wouldn't be any traces on the side. And then to record a trace, you'd click this button here and it would launch the application on your physical device. And so to profile, you have to use a physical device. You can't use a simulator. And so then it would allow you to launch the application on your phone. You could scroll through and profile. And then when you're done, you can stop the trace and Xcode will process it and load it right here. And so this is the output of one of those traces. But before we dig into the trace, let's learn a little bit about how my view works and what might be causing some of the lag before we even start the trace. So I have two different implementations of this view here. The first one is the original implementation that has a lot of lag, and the second one's going to be our optimized implementation that fixes our issues with lag. And so as we look through our application here, we have two main views that we want to be concerned about. So the first one is our stories view. And so stories view is the list of the entire feed that we just saw on the previous screen. And then inside that list, we have a bunch of story rows. And so we have a story row view. And so inside our story row, we have our upvote button, our comment button, and our share button that we saw on that previous screen. So these are the two views we really want to be concerned about. A couple things to note here is that to manage likes, what I'm doing is on my list, I'm storing in state a set of integers, which are the IDs for the stories that I've liked. And so when I like a story, it's going to add to the set of integers. And when I dislike a story, it's going to remove from the set of integers. And then if I jump down to my story row here, when I'm creating a story row, I'm creating the three buttons I have, the upvote button, the comment button, and the share button through escaping closures. And so when you create the story row, you're going to have to pass in closures that create each of these views. And so these are all views I've created right here. And so when you init a story row, you're going to have to pass in the creation of these three different rows. And then we can notice in our upvote button, we actually have a binding to the like stories from our list. And so again, our list has the state, which is the array of like story IDs. And we're passing a binding to that state to our upvote button and to each one of our rows here. So we also have a binding in our rows. And so the reason we do that is so that we can remove and insert identifiers to our like story array. Okay, so now that we have a basic understanding of how that first implementation works, let's go ahead and look at the stack trace and see what's causing all our issues. So when we open up our trace, we're greeted with a screen like this, and it can be a little bit overwhelming because there's so much information on the screen, especially for more complicated apps, it can get really out of hand. And so a couple features that you might want to use are you can drag and select different sections in time of your trace. So you can isolate different sections of your trace to profile. I'm going to go ahead and hit escape and get out of that so we can see our trace as a whole. And so looking at this trace, there's a few things that really stand out to me. One is we have a ton of hitches here. We can see that we're hitching almost all the time constantly throughout this application. The other thing is if we go to the SwiftUI pane here, we have quite a few view updates, right? So we have a ton of view updates. And really, when we're looking at these traces in the SwiftUI section here, we want to really concern ourselves with this top one here, which is SwiftUI itself, and the Hacker News section. So the Hacker News section is updates caused by views within my application, and the SwiftUI section is updates caused by SwiftUI itself, so the SwiftUI library. And so first, let's dig into the SwiftUI one. And so you can see there's a ton of different view updates in here, and even for simple applications, you're going to have a lot of view updates, and it can get a little overwhelming. So there's a few things you want to look out for. In my case, we can see that we have a ton, 231,000 view updates for glass material effect. And so we can see that the duration that this is taking is 850 milliseconds. So this is a ton of time. And if we think back to my view, so I'll jump back to the slides here, we notice that I'm using the glass effect on 3 buttons on every single row. And I have 200 rows. So I'm doing 600 buttons with glass effect. And that's not even including the search bar, the filter button, and the comment button that I have on my tab bar here. So liquid glass is really cool and a really nice feature, but if you're overusing it, it can be pretty expensive on your processor to handle the view and the computation needed for liquid glass. So that's one thing we'll keep in mind when we go back to optimize. We can see that it's 850 milliseconds. So that's a lot of time spent on calculating our glass material effects. The other thing we can notice is in our Hacker News application. So again, this contains updates from all the views in our application. We can see here that we have quite a few updates. So we really didn't perform much. And again, this trace is from that screen recording. So the screen recording and the trace it is the exact same actions performed. So we really didn't perform a ton of actions. We scrolled to the bottom of our screen, we scrolled to the top of our screen, and then we liked 4 comments, and that was it, right? And so just from those few actions, we have almost 3,000 view updates here. So that's a ton of view updates. So clearly there's something wrong here. And clearly we're doing way too many view updates that aren't really needed. And we can drill down and get into a little more detail and see which of our views are culprits. And so all of our views have a lot of view updates here. But the biggest culprit is this upvote button here. And so if you think back to my code, you can remember that I am holding on to a binding from the state in every single one of my upvote buttons. And so just think about that when we go back and optimize. If we want to get a little bit more granular and see what's causing each view update, we can click on this arrow next to our view and show the cause and effects graph. And so this will take a second to load here. And we can see that if we zoom out here, there's a ton of different view updates being triggered by my single upvote button. Like this is a massive, massive graph here. So we have a ton of different view updates being triggered by my upvote button and a ton of different view updates on this side as well. So we can exit out here. And another feature you might want to use, instead of showing the cause and effect graph, you can show updates. And so this will tell you the category of each update. So a lot of creation updates here. Sometimes you'll see skipped updates as well. So that's another thing to watch out for. But we can see that we're probably causing way too many updates, especially in our upvote button and especially in our story row here. And so let's jump back to the application and see and take a look at our code and see what might be causing all these unnecessary view updates. So like I said before, I was kind of giving a hint as to what the problem here is. But in our stories view, so a stories view is the list of all the rows. We have a state, which is our set of all the IDs of the stories we've liked. And so this set is being held onto in every single upvote button and every single story row. So when I make a change to an upvote button, so when I like a story, and this gets executed right here in our upvote button, we're either inserting an identifier or removing an identifier, depending on whether it's already added to our set here. And so we're referencing that state again in our background here. So if our view is one that we liked, so if its ID is a member of our set, we're going to have a blue background. If not, it's going to just have your standard clear background, right? And so every one of these upvote buttons, all 600 of them, or all 200 of them that we have in our application, one for every row, is going to have to update when we like a single row. And so that's obviously not our intended consequence here. So we have 200 view updates every single time we hit a like button. Okay, and so if we want to know how to fix this, we can jump over to our second implementation of our stories feature. So in this implementation, I've changed a few things. First, let's talk about fixing our upvote buttons so that we're not causing that many view changes. And so there's 2 things I did to fix this issue. First, I removed our like story IDs from the state on our stories view. So we can see we no longer have the state for like story IDs. And so that's no longer part of the stories view. Instead, I move that to my state. And so this is an observable state. I'm using the composable architecture from Point Freeco, but this is kind of analogous to an observable object. So I've moved it to my state now. And so that allows us to remove it from our stories view. And instead, when we jump down to our stories view and into our list, so this is where we're using a for each to create every single row in our list. Here in our story row, we've added a new parameter called isLiked. So instead of holding a binding to the state from our list, what we're doing is we're passing in either true or false if the story is liked, and we can handle that logic of calculating if the story is liked in our list itself. So this allows us to update only the views that we're liking. So only the view that we liked updates. So it's 1 view update compared to 200 when we click the like button. All right. So this allows us to get a lot more granular with our view updates. And so when this list is being created, it's only redrawing the views that have changed their likes. Okay. The other thing I've done is, if you notice beforehand, when I was looking at story row on our original implementation, that in our init, we're taking 3 escaping closures here. And each of these escaping closures are creating an upvote button, a comment button, and a share button respectively. So what I realized is that I don't actually need to be taking in an escaping closure here. These views aren't used anywhere outside of this row, so I can just move them to computed properties like this. And so now each of these views is separated out, and I don't need to take escaping closures. And we'll cover later on why having these closures passed into our view or stored on our view can be a little bit detrimental to our performance. Okay. So yeah, we've moved these closures out into computed properties. If you needed to, for some reason, store these closures on your view, what you might want to consider doing is storing the result of the closure on your view instead of storing the closure itself. So if we were to create an init for this story row, what we could do is we could call the closure and store the result of calling that closure on our view rather than storing the closure itself. And so the reason why these closures we really want to avoid storing on our view, especially in state, binding, and environment, is because closures are very difficult for SwiftUI to compare. If you can think about this problem and think about how you might compare two closures, anything can be in a closure body. So how would you compare the two? You only know the types that you're giving the closure and the types that returning from the closure. How do you know if there's unintended consequences of the closure? How do you know what other kind of logic is being performed inside that closure? And so that's why it's really difficult for SwiftUI to compare two views that have closures on the body. So it's still possible, it still works, but it can significantly degrade our performance. And so that's something we really want to avoid. If possible, we want to store the result on the struct. And even better, we can just move them to a computed property or to a separate view. Okay, so that covers most of the changes I made. And now we can jump back. And so running the exact same set of actions on our view, we can see that we have significantly improved performance from this trace. So this trace is with our updated optimized view. We can see here much fewer hitches. If we jump back to our original trace, we have a ton of hitches. Let me expand that. Okay, yeah, so we have a ton of hitches through our application as we're scrolling here. In this optimized view, much fewer hitches. If we jump down into our SwiftUI updates, we can see that SwiftUI still has a ton of updates. But if we look here, our most expensive update, remember, was 850 milliseconds on glass material effect. And so one thing I forgot to cover in our optimized implementation is that I actually removed the glass effect on all of the buttons in the views. So instead of doing glass effect on 600 buttons, I just removed that and am styling the button with other modifiers. So I've removed our glass effects, and we can see that had a huge impact on our performance here. So our glass material effect has dropped from 860 milliseconds to under 100 milliseconds, so over 750 milliseconds less, and much fewer view updates caused by the glass material effect. And so if we collapse that SwiftUI and jump back to Hacker News here, we can see that our views have changed. So they're not exactly the same. So we don't have the same names for all the views here because we've moved the upvote and comment and share buttons into computer properties. But we can see we have much fewer view updates overall on our application. We have 447 view updates as compared to almost 3,000 in our original implementation. Okay. So there's still a lot more work to do here, and it's still a lot more ways we can optimize this application, but this takes care of some of the low-hanging fruit and makes our performance acceptable for release. So that concludes the demo on performance. I'm going to wrap up with a few tips that you can take away from this presentation. So a lot of these are related to performance and just best practices in SwiftUI. Like I said in the performance section, avoid storing closures in view bodies. Closures are very difficult for SwiftUI to compare. And so we especially don't want to store these in the environment, in our state, and in binding, because those will be updated very frequently. We want to avoid conditionals in view bodies. A lot of people create these custom modifiers called apply if or if on that are view modifiers. And so what they'll do is they'll basically take a condition, and then if that condition is true, show a different view. And so we don't, or apply a different view modifier, sorry. So if the condition is true, it'll apply a different view modifier. But that view modifier, so that if-else view modifier, and using if-else statements directly in your view bodies can actually be pretty harmful for performance and animating. So when you're using conditionals, if-else, and view body, each of your branches are added to what's called a conditional content in SwiftUI. And so that makes SwiftUI treat the different states. So like the view that's evaluated in the if body and the view that's evaluated in the else body as separate views with separate identity. And so I didn't cover identity in this talk, but view identity is a very important topic. And so if we change the identity of our views, that can break things like animation and can cause performance issues. So we want to avoid using conditionals in view bodies if possible. Instead, what we can do is a lot of view modifiers in SwiftUI take optionals. So we can use a ternary and pass nil to a view modifier rather than using if and else in our view bodies. The next tip is to, when you're optimizing, first minimize the number of state updates you're making. So you can use Xcode 26's new SwiftUI instrument and really cut down on the number of state updates you're making. And then you want to minimize the work being done in each state update. So we wanted to have really efficient state updates, and we can actually offload some things into the background if we need to when we're updating. Like we saw in our performance demo, avoid overusing expensive views. So not all views are created equal. Certain effects you add to views, such as liquid glass, can be very computationally expensive and cause performance issues with our app. Avoid using the ID view modifier. A lot of times I see the ID view modifier used as a hacky way to kind of fix an issue that someone's seeing, but oftentimes that's kind of a band-aid on a bullet wound, and the ID view modifier can cause issues with your animation and performance later for the same reason that using if and else can, because you're creating different views, so you're changing the view identity, and view identity is how SwiftUI can track your views, so you're breaking the tracking with SwiftUI. Like I harped on a bunch in the beginning of the presentation, you should always make state private and initialized. Don't use state like binding. State should always be local to a view. If you need to pass state between views, you can use binding, or you can use our next tip, which is using observation. Observation is extremely efficient. So if possible, if it makes sense in your application, use observation either via observable object or the observable macro. And then finally, this one is the oldest advice in UI programming, but work that doesn't require the main actor should be executed in the background where possible. I have a typo on there, but it's work that doesn't require the main actor should be on the background. You don't want to do what the bullet point says there. That can really slow down your application. So if you have expensive work on the main thread, all your UI is kind of computed on the main thread. So if you're slowing down the main thread, you can really slow down animations and slow down transitions in your application. Okay. I have some sources here for where I pulled a bunch of the information for this presentation. Also, if you're interested in the view modifiers I use to create the visuals, I'm going to be posting a public GitHub repo where I have that mirrored view modifier. I have view modifiers for visualizing alignment guides. And I can show some of that after the presentation as well if anyone's interested. But that wraps up my presentation. That's all I had today. Thank you so much for listening. Now I think we can open the floor for questions.
There's a few questions in the chat, so I'll read them through. These were coming in during the session. So the first one from Gus was why two tuple views?
Why two tuple views? It's a good question. So we'll jump back to the question here. I think actually this might have been, so like I said, I had a view modifier that kind of creates these, or it's not a view modifier, but it's a view that creates these trees here. And I think when I was creating them, I couldn't figure out how to like parse that second view or that tuple view out of there. I wasn't exactly sure how that was getting picked up. So I'm not entirely sure if that's accurate. It might actually only be a single tuple view. I'm pretty sure it's only a single tuple view that should be in that view tree there, but I think that's an issue with the view modifier that I should have pointed out beforehand. But yeah, that's a good question and a very good observation.
All right, from Sean, is the attribute graph cyclic or acyclic? How does SwiftUI handle cycle when attribute A depends on B and B depends on A?
Really advanced question, and I unfortunately don't know the answer to that. You might have to ask Apple themselves. I'm sure there's some like testing you could do to figure out how that works and how it handles cyclic dependencies. But unfortunately, off the top of my head, I don't know the answer to that question. There's actually a bunch of really good tools online. There's one in particular that you can use to get the attribute graph for your application. And so if I jump to that slide where I had the attribute graph right here, that's actually from one of those tools. So there's actually a macOS app you can install that will show you the attribute graph for your application. And if you're interested in finding out how the attribute graph handles cyclic dependencies, that's probably how you would do it.
All right, and then the final question we currently have from Jason is, would we have the same level of efficiency if our view had assignable view builder properties instead of basic closures?
So the question is, if you had assignable view builder properties instead of basic closures.
So I think this is back to your example. Would you have the same level of efficiency there?
Okay, so Jason, you're saying if I change these to be view builders, is that the question?
I'm gonna quickly change the settings so people can unmute. Okay. Okay, that's fixed.
You're
Yeah.
exactly right. So we can assign upvote button as a view builder property. So
Mhm.
externally, then we could dictate it instead of having a closure. But I'm wondering what the performance is compared to your example on the right, where it's internally declaring those view builders.
Mhm. Yeah, so I think either way you're storing a closure, adding the view builder annotation to that closure isn't really going to have too big a difference on performance. Um, because either way you're going to be storing a closure on that view no matter what. That would be my understanding. I haven't actually tried that. So I haven't done that in the demo. I can actually, after this presentation, kind of play around with that because I'm interested if there is a difference in the two. I would venture to guess that there isn't a difference because either way you're storing a closure and that's going to be difficult to compare on your view. So that's my best guess. I'm sorry I don't have a better answer for that. But yeah, I'm definitely interested in what the performance implications are to adding that annotation. So I'm probably going to run a trace after this and see if there's any difference.
I think part of the line transfer feature of Capital One's app is doing that in places. If you want to
Mhm.
look at that.
Yeah, definitely. And the idea for that tip actually comes from an Apple session that's really good. I've linked it in the sources. And so they talk about how closures are difficult to compare, and they actually go through the same process of optimizing an app for performance using SwiftUI tools. So yeah, it's a really common thing. And I hadn't thought about it before that talk, but it really makes a lot of sense when you think about it, because how can you compare two closures? And so it's that you're really giving a difficult task to SwiftUI to track these view updates here. And so especially when you're storing things in state, a lot of the time it can just be very easy to store a closure on your view, but that might have some unintended consequences. And so you might want to consider just storing the result there. So yeah, good call, Jason. I'll make sure to do that.
All right, any other questions?
Yeah.
Maybe a bit of a tangent, but I think in the glass, in the talks about glass from this year, there was some recommendation that I've not personally used, where the idea is if you have you have the glass effect modifier applied to three distinct views, it is more expensive than using a container to apply a single glass effect. Have you experimented with that at all?
I have not. So I did see a couple talks from Apple about liquid glass and how to optimize the performance. I can imagine that's the case. That's definitely something to add here too. For this demo, the first implementation is something I would probably never actually write. Like some of the examples are a little overblown just to demonstrate the point. But really, the goal of it was like to try to make the most inefficient app that I could think of. That's very simple, and then we can use that to demonstrate the profiling capabilities provided by the SwiftUI instrument. So yeah, I haven't tried that in particular. That's something I do want to try out with this app. Now that you pointed out, I think it would be pretty insightful to see how that compares. But yeah, I can imagine it would be a lot more performant than having three separate glass effects for every row.
Do you find that the cause and effect graph is ever flaky for you? It like worked remarkably well in your example.
Mhm. Yeah, so this is an application that I've created just for the purposes of this demo. So there's really not a lot of code, not a lot of views going on here. It works flawlessly. Like Xcode always works flawlessly with your simple applications. And then when you get to enterprise scale things, things can break down. So I haven't noticed it necessarily saying anything wrong, but it can be very laggy. Like you saw, even with my very simple view, I had a lot of updates, but when I was going to the cause and effect graph, it took a while to load. And so when you're in a larger scale application, it can take a really long time to load that. So much so that it like kind of just breaks my focus and I switch to something else. But also, one thing too with large applications is your cause and effect graph can be really large, and it can kind of be a little bit misleading because it might not be that you're causing an unnecessary number of view updates. It's just that you have so many intertwined views that those view updates are necessary, if that makes sense. So yeah, I haven't seen anything like particularly wrong with the cause and effect graph. I think with small applications, it's really useful. If you can, if you have a larger application, if you can kind of use smaller views or like kind of isolate your views if you want to test performance, I think that's probably the best way to go because it makes things a lot more easier to read and it kind of isolates the problem too. If you have a lot of like very polluted dependencies, it can be very difficult to understand where your performance issues are coming from.
Can you go to the tip slide once?
Sorry, which slide?
The last one, we have tips, right? Like,
yeah.
So do you think like some of those would apply for the build times as well?
Sorry?
Do you think like some of those would apply for build times as well? You measured performance, right? Like before and after.
Yeah.
Do you think like would they apply similar for build times as well? Like, before and after like these changes?
Yeah, really good question. So yeah, when I was talking about performance, I was mainly talking about runtime, but your question is very good about build time as well. And so as far as the ones on here, the ones that would affect build time specifically on this would probably be observation. Because observable is a macro if you're using the observable macro. A lot of us don't have access to the pre-built Swift syntax binaries, so that can really bloat your build times if you're using macros. So that would be one to watch out for. If you're really worried about performance and you don't have access to using the binary Swift syntax, I would recommend maybe just going back to observable object for a little bit. I don't see any of these specifically called out on the slide that would really have a catastrophic impact on your build times. One thing to watch out for is everyone that has used SwiftUI and done more than a demo has run into the compiler cannot type check this expression with SwiftUI. That's probably the most complicated error you get. And so really what that means is that there's an error somewhere in your view, but you have such a long view body or such a complicated view body with so many different branches that SwiftUI can't type check it. And so it makes the error reporting bad because we don't have a direct error line, right? It just kind of says for the overall view that it can't type check it. And so one thing that would help with that is probably the conditionals help a lot with that. Also, like you saw in my performance example, breaking things down into computed properties really helps. And so as a general rule of thumb, if your view body gets too long, so if I ever have to indent more than 3 times, what I do is I break it out into a separate view. And so if that subview needs to be used in other places, I make it a view struct. So I actually create a whole new view. If that subview is only used in the local view I have, then I make it a computed property. And so that's kind of how I handle those two things. Yeah, as far as compilation time, the thing you really want to watch out for is Swift syntax. I don't think there's anything in here that would I'm sure there's differences between compile time, but the only one that would really make it very noticeable for you is using macros because that's going to have to pull in Swift syntax. So yeah, the main thing is getting accurate error reporting, which is what I was talking about with the cannot type check this expression in time. Yeah, but good question. Thank you. Go ahead.
Was there any hint in the profiling for specifically to the closure that you added for the buttons?
Yeah, good question. It's kind of difficult to see in this. I don't actually know if it would really. Okay, so this is a new feature to SwiftUI, and I haven't played around with it, or to Xcode. So I haven't played around with the SwiftUI instrument enough to see how you would specifically see that in your profiling. I guess we could see, so the place I would start to look, and so in this application, because it's so simple and because those closures are so simple, I don't really think it's going to have a big performance hit, but it's something I wanted to call out because in bigger applications it can. But if we were to try to find out where that was, if we were having real performance issues because of that, I would guess you want to look in your long view body updates right here, and in your update group. So it's going to be somewhere under the SwiftUI, probably in your long view body updates here.
What is, I mean, I see long view body updates, but I don't know what exactly it represents.
Yeah. So okay, let me highlight this. Okay. Yeah, so we can click around on this timeline here. So this is a timeline of our application as we're running through the trace. And so we can see in red here, it's marked where our view buddy updates are taking longer than expected. So when they pass a certain threshold, they'll show up in your instrument here. And so we can click on these different updates and we can actually let me see if I can remember how to get there. There's actually a way to look at the call stack at this point. Yeah, I forget exactly how to get there, but there is a way that you can look at and see like what's causing your long view body updates by looking through this timeline.
You said we can't use the SIM for profiling?
For SwiftUI profiling, you have to use a physical device if I'm not mistaken. So that's why I have my phone actually plugged in here so I could show that. If I unplug my phone, drop my laptop there, you can see that it actually won't let us profile. So I'm going to hit Command I to build for profiling. Well, actually, it will because it's connected to my phone regardless of the cable. But if I try to do it on a simulator here, we're going to need to it won't actually. So you'll get up to the instruments page. And then when you go to launch it, it's going to say you need a physical device to profile for SwiftUI. So we jump in here. And we can see here that we don't even have the run button because we're on a simulator.
Interesting.
Any other questions?
Great presentation. Thank you.
Thank you. Okay, awesome. I don't think I see anything in chat either. So I can hand things back over to Scott. Thank you all for listening.
All right. Thank you, Will. Great talk. With that, it's time for, usual close up, usual announcements. If you're interested in speaking, let me know. I can send you the link to the forum directly. Subscribe to our YouTube channel to get this video as well as watch all other videos we've had, minus the 1 year, which I still have not been able to finish recovering. Again, follow our LinkedIn page for our primary information. That's going to be the best place to keep track of when we have not only iOS meetups, but Android, Flutter, meetups in New York, and just some other things. There might be some exciting cross collaborations coming soon. And then for everyone here, I have stickers. All right. Next month, we are going to have a remote speaker. Leo is going to come talk to us about vibe coding, a skeptic's guide to finding your rhythm in AI-assisted development. For those here in McLean, in the DC area, we'll be back here as usual. But again, as usual, we will always be on Zoom. And with that, that calls it for the night. Thank you, everybody. Have a good day. See you all next month, and thank you for your time.
Thank you. Great job, Will. Thank you. Great job. What's the best way to